Hi, and welcome along to episode 4 of the Engineering Street. Today, we will be talking about the engineering behind the Perseverance Rover on Mars.
On July 30th, 2020, a United Launch Alliance Atlas V rocket lifted off from Cape Canaveral, Florida, carrying the next generation of Mars exploration vehicles, the Perseverance Rover and the Ingenuity helicopter. And earlier this week, on February 18th, 2021, the two vehicles had completed their long 7-month journey to the red planet successfully. Only about 40% of missions sent to Mars have ever been successful.
The Perseverance Rover is the largest and heaviest rover JPL has ever sent to Mars, heavier than the Curiosity rover by 100 kilograms. With that extra weight comes a whole host of new gadgets. This is not just some slightly updated version of the Curiosity rover, however. Perseverance is benefiting from almost 10 years of technological advancements, and it is packed with fascinating and novel technologies that will form a stepping stone in humankind's eventually first steps on the surface of the red planet.
Perseverance is now safely on the ground, where it will spend a long and meaningful time on Mars. We have learned some things from the Curiosity rover that will hopefully help Perseverance avoid the struggle its predecessor is experiencing.
We are already aware of the struggles of the Curiosity rover wheels and how they have been gradually degrading on the harsh Martian surface. In the end, the engineers at JPL did not opt to shape the memory alloy wheels, but instead they came up with a rather simple solution.
They very simply decided to increase the diameter of its wheels, decrease the width, and increase the thickness, while incorporating sturdier curved threads that will better resist crack growth than Curiosity's sharp cornered threads. They've also forgone the rectangular cutouts which imprinted Morse code, spelling out Rover's origins in the rusty dirt of its new home.
There are a whole host of new software updates too, like the algorithm that determines when to open the parachute. In the last mission, the parachute simply deployed when the target speed of 1,450 kilometers per hour was reached, after most of the hypersonic re-entry speed of 21,450 kilometers per hour had been bled off.
For Perseverance, JPL wanted to increase the accuracy of the landing, so this time around, the chutes will open when it's approaching the optimal trajectory for the landing site. It will also be scanning the surface of the landing site and correlating those images to its pre-existing map to allow the sky crane to choose the best landing site with minimal obstacles.
Perseverance's ground navigation systems have also been significantly upgraded, with its optical sensors feeding data to a machine learning vision algorithm, allowing Perseverance to find its own path through the rough terrain of Mars, where Curiosity had to constantly stop and start and stop and start again with help from its earthbound controllers. This way, the whole mission can be controlled directly from the surface of the planet Mars.
Perseverance is benefiting massively from the past decade of improvements in autonomous flight and driving developed by the drone and automotive industries. This will mean Perseverance will be able to cover much more ground in its life here in Jezero Crater, a massive crater that was once home to a lake the same size as Lake Tahoe.
You can see there are remnants of this ancient riverbed and deltas spilling into what may have been a once habitable body of water. It is here that Perseverance will scour for signs of life. However, before we get into all the gadgets it will use to do this, let us look at how Perseverance will power them.
The Perseverance rover features the same radioisotope thermoelectric generator as the Curiosity rover. RTGs, or radioisotope thermoelectric generators, work by converting the heat from the natural decay of a radioisotope into electricity.
It uses a simple principle called the Seebeck effect to generate electricity. The Seebeck effect essentially allows us to generate an electric current through a heat differential as charge carriers. Both electrons and electron holes will move from hot to cold. So, if we have two semiconductors, one with the charge carried in the form of electrons and one with the charge carriers in the form of holes, the potential difference between the two semiconductors will form when a heat gradient is applied. This potential difference causes a current to flow in the external circuit. These two semiconductors need to be both thermally insulating to ensure that this heat gradient is maximized, but also electrically conductive to maximize the current.
These two material properties are typically linked. Copper is both a great electric and heat conductor, while iron is a poor electric and heat conductor. Having a single material that is a great electric conductor and a poor heat conductor are extremely rare.
For this reason, two unique materials are used for the P and N-type semiconductors. Lead telluride for the N-type and an alloy commonly called tags for the P-type, which is formed from tellurium, silver, germanium and antimony.
Now we just need a consistent heat source. Thankfully, radioactive substances generate heat as they decay. The Perseverance Rover (RTG) uses 4.8 kilograms of plutonium dioxide as its heat source. This radioactive material primarily produces alpha waves, which is essential, as this form of radiation is most efficiently converted to heat in a compact space, while plutonium-238 also releases minimal beta and gamma radiation, decreasing the weight of shielding needed to protect the electronics on board from these more powerful kinds of ionizing radiation, an essential characteristic for a lightweight spacecraft. The plutonium-238 is also formable into a ceramic-like material that will break into large chunks, rather than being vaporized and spread in the wind during a launch failure, where it could be inhaled or introduced into the food chain.
The electricity this unit can provide will gradually degrade from its maximum of 110 watts at launch, as its plutonium heart naturally decays, losing half of its energy every 87.9 years, which is much longer than the 138-day half-life of the early polonium-210 RTG prototypes. Another advantage of plutonium-238 for this application is that it will power all the instruments on board, like the MOXIE instrument, which is one of the new devices we are most excited about aboard the Perseverance Rover. MOXIE is a new oxygen generation device that will test a vital technology for any future human mission to Mars.
You may wonder, like we did, how is this different from the oxygen generation present in the International Space Station? There is obviously a limited supply of oxygen there. Why do we need to test this new technology on Mars when we have obviously tried and tested methods of creating oxygen already?
The International Space Station does not really recycle oxygen. Oxygen is created on the International Space Station through the electrolysis of water. This produces hydrogen and oxygen. The hydrogen is then reacted with the carbon dioxide to form water and methane. The methane is simply exhausted into space while the water is fed back into the system. The International Space Station requires regular resupply of water, as we are losing 2 hydrogen atoms for every oxygen molecule we create.
This is not a closed-loop system, and water is a pretty heavy material to be shipping to Mars. The Perseverance Rover will test a new method of oxygen creation, using this device, which will be solid oxide electrolysis, to instead break the plentiful carbon dioxide in the Martian atmosphere into oxygen and carbon monoxide.
Its operation is fairly simple. Air will be taken in through a dust filter by a specialized pump designed to be as light and compact as possible, called a scroll pump. Scroll pumps are pretty cool. They consist of 2 spiral coils, one stationary and one rotating. Air is taken in at the inlet here, and as the secondary scroll rotates, it traps in air and squeezes it against the primary stationary coil. This continues to happen as the volume between the two scrolls decrease down the spiral, causing an increase in pressure. In this case, it takes the variable pressure Martian air, which is typically about 100 times lower than the Earth's atmosphere, and compresses it to match Earth's sea level pressure. These kind of pumps are lightweight, energy efficient and reliable, making them the perfect air pump for the Perseverance Rover.
The pump feeds the carbon dioxide-rich air through a cell stack. Each stack consists of a catalytic cathode, a solid electrolyte, and an anode. As air passes over the cathode, which operates at 800 degrees Celsius, the carbon dioxide is split into carbon monoxide and oxygen ions. According to this reaction, the oxygen ion passes through a solid electrolyte to the anode where it's oxidized, combining with a second oxygen atom to form the gaseous O2, which is then passed out of the anode cavity and tested for purity.
MOXIE can produce 20 grams of oxygen an hour. However, the unit will not run continuously as it draws too much electricity, which will be needed for other operations. B will highlight RTG, MOXIE and batteries. We are not sure where the batteries are located. The total system needs 168 watts, which is actually more than the 110 watts the RTG can provide at any one moment. So this operation will need to be supplemented by the 2 lithium-ion batteries that are included on board to make up for the lower power RTG, allowing it to store excess power during downtime.
This device is exciting because this is a clear statement of intent. Oxygen is going to be a vital resource for any future human mission, and this is actually a scaled-down prototype of the full-size version NASA eventually wants to send to Mars, along with an empty rocket. The full-scale version will produce about 2 kilograms per hour, which will gradually be stored inside the awaiting rocket over the course of a year and a half, providing life-sustaining air for any human mission in the future and the oxidizer needed for the ride home.
Device, which is also dependent on a future Mars mission is to complete its purpose, is the core sampling drill. The Curiosity rover sampling system drilled and scooped soil into this instrument, the SAM, standing for Sample Analysis at Mars. The SAM is located here on the rover. It contained multiple tools that would be commonplace in many of Earth's earthbound labs: a mass spectrometer, a gas chromatograph, and a turntable laser spectrometer, each looking for different signs of life on Mars. Perseverance has replaced the space this unit took up with a totally new system, the sample catching system. The robotic arm of the rover features a coring drill which will cut out cylindrical core samples from the Martian surface. Once collected, the robot's head mates with the drill bit carousel, where it transfers the bit and the sample tube into a rotating carousel that takes it to the belly of the rover, where another robotic arm resides.
Here, a number of operations take place. First, the arm pulls the sample tube out of the drill bit. and takes multiple images of it before and after calculating the volume of the sample. Then, it stores it in one of the 42 slots under the belly of the rover, where they will remain until the rover deposits them in the sample tubes at a designated catching spot on the Mars surface.
There are plans to send another rover, designed by the ESA, to Mars in 2026. This rover will deliver the samples back to its NASA-designated lander, which will then load them into a Mars ascent vehicle, blasting the samples into orbit, where the ESA Earth Return Vehicle will be waiting for it. We are attempting to bring soil back from Mars with robots, and if that isn't insane engineering, I don't know what is. And we've barely scaled the surface of what this rover is capable of.
There's a whole host of new sensors on board that don't require Perseverance to collect soil, each using different forms of electromagnetic radiation to investigate the ground below them. Their Sherlock instruments on the robotic head will look for signs of biosignatures using Raman and luminescence spectroscopy, which both detect molecules based on how they interact with UV light. It will sit about 5 centimeters off the ground, where it will focus its UV laser onto the soil and be able to detect chemicals that would indicate the presence of past life.
An X-ray imager called the Pixel that will be able to visualize the texture of the ground below. It is looking for tiny variations in geology that would indicate that microbial life has altered the environment, while also being able to detect chemical compositions by observing the fluorescence of the target under X-ray electromagnetic radiation.
There are several other sensors, like the ground-penetrating radar imager, located at the rear of the rover, which will give us visualizations of the composition of geology up to 10 meters under the surface and possibly even identify water and resources buried below, a vital resource for future human missions.
These are just some of the sensors aboard, and of course there are the usual high-definition color cameras that are going to send back amazing images to Earth, and we included a microphone so that we will be able to hear what our future life on Mars may sound like. It may even catch the whirring of the helicopter blades off in the distance, because by far the most exciting part of this mission, for us, is the Ingenuity helicopter. After all, if successful, this will be the first time humans will have demonstrated controlled powered flight on another planet.
Powered flight on Mars presents many challenges. The atmosphere is about 1% the density of Earth, meaning there's less air to push down to achieve lift. To combat this, the propeller blades, which are counter-rotating to eliminate the need for a tail rotor, spin much faster than traditional helicopter blades at about 2,400 RPM.
That is around 5 times faster than an equal-sized RC helicopter, remote control helicopter, here on Earth. To deal with the centrifugal forces that come with that, the blades need to be made of a high-strength carbon composite. These blades also have a much larger angle of attack than your run-of-the-mill blade, allowing them to push a larger volume of air downwards.
Since this helicopter will detach from the Perseverance Rover, it needs its own power source too. Unlike the planned Dragonfly mission to Titan, this helicopter will not have its own RTG. Creating an RTG capable of fitting into this 2-kilogram helicopter is unfeasible. Instead, it features these solar panels, which will charge 6 lithium-ion batteries on board, and these in turn will power the motors and cameras aboard for a max flight time of about 90 seconds.
This is simply a technology demonstration that will hopefully give NASA and JPL the information they need to approve and design a future flying rover. Thursday the 18th of February 2021, a day that will go down in history forever.
Thank you for watching this week's episode of The Engineering Street. Comment down below whether or not you think we'll find signs of life on Mars.
Don't forget to like, share and subscribe. And as always, see you again soon.